Right now, every power plant, every solar farm, every nuclear reactor, and every wind turbine on the entire planet combined produces roughly 18 terawatts of energy. That sounds like an enormous number until you compare it to the threshold scientists use to define a truly advanced civilization, one that has learned to harness the full energy potential of its home planet. That threshold sits about 1,000 times higher than everything humanity currently produces combined. We are, by the most widely used measure of civilizational advancement in all of science, still stuck firmly at what's called Type 0, and there's a very real chance we may never fully climb out of it. I'm the host here at Today Latest Analysis, and today we're breaking down the Kardashev scale, the framework scientists use to measure how advanced a civilization actually is, where humanity genuinely stands on it right now, and why some researchers seriously question whether we'll ever reach the next level at all. Subscribe now, because we cover real science exactly like this, the concepts that explain the biggest questions about our place in the universe. Let's start with where this entire idea came from. In 1964, Soviet astrophysicist Nikolai Kardashev proposed a deceptively simple way to rank the advancement of any civilization, not by its art, its politics, or its population, but by the one resource every technological society fundamentally needs more of: energy. Kardashev defined three basic categories. A type 1 civilization has learned to harness essentially all the energy available on its home planet, something on the order of 10 to the 16th power watts. A Type 2 civilization has gone a level further, capturing the entire energy output of its own star, roughly 10 to the 26th power watts for a sun-like star, an amount so large it would typically require some kind of massive orbital infrastructure surrounding the star itself. And a Type 3 civilization operates on a scale that's almost impossible to picture, harnessing the energy output of an entire galaxy, somewhere around 10 to the 37th power watts, a difference so extreme between each level that it's less like climbing a staircase and more like jumping between entirely different orders of physical reality. It's worth pausing on just how enormous the gap between these categories actually is, because the numbers alone can slide past without really registering. Moving from Type 1 to Type 2 isn't a modest 10-fold or 100-fold increase in energy use. It's a jump of roughly 10 orders of magnitude, 10 billion times more power. Moving from Type 2 to Type 3 is another jump of similar scale on top of that. To put it in more human terms, the difference between a Type 0 civilization like ours and a genuine Type 1 is already roughly a 1,000-fold gap in total energy production. The difference between Type 1 and Type 3 combined is closer to a trillion-fold increase. These aren't neighboring rungs on a ladder. Each category represents an entirely different relationship with the physical universe, which is exactly why, more than 60 years after Kardashev first proposed this scale, humanity remains stuck firmly within the very first, smallest category of the three. Kardashev's original three categories were useful, but they were also a little too simple for scientists trying to place real civilizations, including our own, somewhere on the scale. That's where astronomer Carl Sagan came in, proposing a continuous, fractional version of the scale using a straightforward logarithmic formula based on total power consumption, allowing a civilization to sit at a specific decimal point between the major categories rather than being locked into just three rigid boxes. Using Sagan's version of the scale, researchers can calculate exactly where humanity currently sits, and the answer is consistently landing somewhere around Type 0, 7 to Type 0. 73. Here's what that number actually means in practice. A 2023 study led by Antong Zhang, a visiting researcher at Harvard's John A. Paulson School of Engineering and Applied Sciences, used economic, demographic, climate, and ecological variables to calculate humanity's precise current standing at Type 0, 7276. The same study projected that by the year 2060, continued growth in energy consumption would push humanity up to roughly Type 0, 7449. An increase of about 50% in total energy use, but still nowhere close to full Type 1 status. As Zhang put it directly, quote, "Under current energy and technology trends, reaching Type 1 civilization status would likely take millennia, unless major breakthroughs, such as large-scale renewable expansion or nuclear fusion, substantially change the trajectory. Millennia, not decades, not centuries in the optimistic case, potentially thousands of years under the trajectory we're currently on." It's worth understanding just how much progress humanity actually has made to get even this far, because it puts the remaining distance into perspective. Roughly 120 years ago, at the dawn of widespread electrification and industrial power generation, humanity sat at approximately Type 0, 58 on this same scale. In just over a century, industrialization, electrification, and the fossil fuel era pushed us up to roughly Type 0, 72 today. That's genuinely significant progress by any historical measure, and yet the distance remaining between Type 0, 72, and a full Type 1, a civilization that has mastered its entire home planet's energy budget, dwarfs everything humanity has accomplished across the entire industrial age combined. So what would actually closing that gap require? Reaching Type 1 would mean humanity fully transitioning away from fossil fuels toward a combination of renewable sources and, most plausibly, functional large-scale nuclear fusion, the same basic reaction that powers the sun itself, finally becoming a practical, everyday source of essentially limitless, clean energy here on Earth. It would likely require space-based solar power, arrays of solar collectors positioned in orbit where sunlight is constant and unfiltered by atmosphere, beaming that captured energy back down to the surface using microwaves or lasers. It would require entirely new global energy storage systems capable of holding and distributing that scale of power without massive losses. And underneath all of that pure engineering, it would require something far harder to build, a level of coordinated global governance and economic restructuring capable of managing planet-wide energy resources equitably, sustained not for a single election cycle or a single generation, but continuously across many decades. As one recent analysis of the scale put it plainly, the hardest part of reaching Type 1 was never really going to be the engineering. It's sociological, maintaining multi-century projects and priorities in the face of political fragmentation, climate stress, economic inequality, and the simple unpredictability of human nature over that kind of timescale. If Type 1 ace already looks nearly impossible on any reasonable near-term timeline, Type 2 sounds like pure science fiction. And yet, it's exactly the kind of civilization astronomers have spent real telescope time actively searching for. A Type 2 civilization capturing the full output of its own star would most plausibly do so using something called a Dyson swarm, a term based on physicist Freeman Dyson's original 1960 proposal, a massive collection of solar collectors, habitats, mirrors, computational nodes, and industrial platforms, all orbiting a star closely enough to capture a significant fraction of its total energy output. Importantly, most serious modern analysis of this idea doesn't picture a single solid shell built around a star, the popular science fiction image, but rather a gradually expanding swarm of independent structures that, over enough time, coalesces into something that functions the same way. Whatever practical form it took, one law of physics makes a Dyson swarm theoretically detectable from enormous distances away. Energy that gets captured and used eventually has to be released again as waste heat, and that heat radiates outward specifically in infrared wavelengths. A star wrapped in a partial Dyson swarm would look strange to an outside observer, dimmer than expected in visible light, since much of its light is being intercepted and used, but unusually bright in the infrared, since all that captured energy still has to go somewhere once it's been used. That specific signature is exactly what astronomers have gone looking for. Researcher Jason Wright led a project known as GHAT, short for Glimpsing Heat from Alien Technologies, using data from the WISE Space Telescope to scan roughly 100,000 nearby galaxies for exactly this kind of anomalous infrared excess, a signature potentially consistent with a Type 3 civilization operating on a truly galactic scale. The results came back essentially empty. No galaxy in that survey showed the unmistakable signature scientists were looking for, though a small number of individual stars elsewhere have shown unexplained infrared excess worth further investigation, with natural explanations still considered far more likely in every case examined so far. The most famous individual case connected to this entire search is a star known as KIC 8462852, nicknamed Tabby's star after astronomer Tabitha Boyajian, whose team at Yale first identified its bizarre behavior back in 2015 while combing through data from NASA's Kepler Space Telescope. Tabby's star exhibited deep, highly irregular dips in brightness, in some cases dimming by more than 20%. Unlike anything a normal planet passing in front of its star could ever produce. For a genuinely electrifying stretch of time, a partial Dyson swarm under construction was floated as one serious possible explanation among scientists, not dismissed outright as fringe speculation. Subsequent, more detailed observations eventually found that the dimming affected different wavelengths of light in ways more consistent with an uneven, drifting cloud of natural dust, likely the debris from a family of comets, rather than any artificial structure. The natural explanation ultimately won out. But for a brief moment, one ordinary-looking star genuinely had the world's astronomers seriously entertaining the possibility they'd stumbled onto direct evidence of an advanced alien civilization. And the search for stars behaving the same way hasn't stopped since. There's a separate, less commonly discussed alternative to Kardashev's energy-based ranking worth understanding too, proposed by physicist John Barrow in the late 1990s. Rather than measuring advancement purely by how much energy a civilization consumes on an ever-expanding outward scale, Barrow suggested ranking civilizations by their mastery of miniaturization and control over increasingly small scales of matter, moving inward toward manipulating individual molecules, atoms, and eventually the fundamental particles and structure of space-time itself. Barrow's scale runs, in a sense, parallel to Kardashev's, one climbing outward toward stars and galaxies, the other climbing inward toward atoms and the Planck scale, offering a genuinely different lens for imagining what true technological advancement might ultimately look like, beyond simply consuming ever larger quantities of raw energy. All of this connects directly to one of the most unsettling open questions in all of science. A puzzle physicist, Enrico Fermi, is famous for articulating simply as, "Where is everybody?" Given the sheer number of stars in our galaxy alone, and the fact that many of them are billions of years older than our own sun, basic math suggests that if advanced, energy-hungry civilizations are common, at least some of them should have had more than enough time to expand, colonize, or at minimum leave some detectable technological signature somewhere across the galaxy by now. And yet, despite decades of dedicated searching through SETI, the search for extraterrestrial intelligence, and more recent infrared surveys like Project G-HAT, specifically hunting for Dyson swarm signatures, we found nothing. Not one confirmed radio signal, not one confirmed infrared megastructure, not one unambiguous sign that any other civilization anywhere has ever climbed meaningfully higher on the Kardashev scale than we have. That silence has led some researchers to a genuinely sobering hypothesis known as the Great Filter, a concept proposed by economist Robin Hanson. The basic idea is that somewhere along the long evolutionary road from simple chemistry to a Type 3 galactic civilization, there exists some kind of barrier, some improbable step that overwhelmingly prevents life from making it all the way through. The deeply uncomfortable part of this idea is that nobody knows whether humanity has already passed that filter or is still approaching it. If the filter sits behind us, somewhere in the improbable jump from simple chemistry to the first living cell, or from single-celled life to complex, intelligent organisms, then humanity may already be one of the rare exceptions that made it through, and our future among the stars could genuinely be wide open. But if the filter still lies ahead of us, the explanation for that silence across the galaxy could be something far darker, a barrier every sufficiently advanced civilization eventually runs into and fails to survive. Nuclear weapons capable of ending civilization in an afternoon. Engineered pathogens capable of spreading faster than any natural disease in history. Runaway climate change destabilizing the very planet a civilization depends on. Or increasingly, artificial intelligence systems advanced enough to outpace the ability of their own creators to meaningfully control them. Every single one of those risks happens to be a challenge humanity is grappling with directly right now in this exact moment of our own climb up the Kardashev scale. So where does that actually leave us? Stuck at roughly Type 0. 72, having made genuine hard-won progress over the past century, but still separated from full Type 1 status by a gap that current trends suggest could take millennia to close, unless a genuine breakthrough in fusion power or global-scale renewable energy fundamentally changes that trajectory. Type 2 and Type 3 remain for now purely theoretical categories, defined with mathematical precision but with no confirmed real-world example anywhere in the observable universe, despite genuine, serious searches using some of the most powerful telescopes humanity has ever built. Whether humanity ever climbs meaningfully higher on this scale may ultimately depend less on any single scientific breakthrough, and more on something far more fundamental, whether we manage to survive the very technologies we're currently developing long enough to actually put them to full planet-scale use. I'll bring you the next update the moment any new candidate Dyson swarm signature or any meaningful breakthrough in fusion energy gets seriously reported by the scientific community. If you want real science explained clearly, connecting the biggest questions about civilization and the universe to actual published research, that's exactly what we do here every time a story like this comes up. Drop a comment and let me know what you think. Is the great filter behind humanity, or still ahead of us, waiting somewhere further up this same long climb? Subscribe so you don't miss the next update. Share this with anyone who'd find real questions about our civilization's future genuinely fascinating, and I'll see you in the next one.